In this video, we will talk about time in distributed systems. Let us first see how time in these systems usually work. So let's say you have your computer here, okay, and it has some time t1, okay. So this computer would have its own time which would be running at some speed x1, okay, and then this computer will try to sync the time from time to time and check with other computers which have the actual time, okay. So one of the ways or protocol that is commonly used is NTP, okay. NTP has systems at different levels like level 1, level 2. They use some different terminology, but the thing here is level 1 would have the perfect time. Level 2 nodes are synced with level 1, so they might have little bit of drift, and level 3 might be getting time from level 2. So this is just an overview. So now let's see why physical clocks, the wall clock we have or the clock in the system itself, why they are not reliable. So one of the thing is they are synced over network. As you see in this example, right, we make a request to check the time and we get a response. If this network is not reliable, there is a delay in this network, we'll get a different time. So due to this, our local clock might jump forward or it might even jump backwards. So that's why these clocks are not reliable, okay. So there are two ways the clocks can be inaccurate. One is the clock skew, which is just defined as what is the true time. Let's say actual time is t2 and our time is t1, and what is the difference between these two, t1 and t2. So that is the clock skew. Another is the clock drift. Usually people think they both are the same thing, but they are different. So clock drift is when your clock is running faster or slower than it should. So over time it would either gain some time or lose it. So clock drift will eventually cause clock skew, okay. That's how your computer clocks might have issues, and that's why physical clocks are not reliable. Since physical clocks are not reliable, we need a mechanism to deal with things like event A happened before B. So this brings us to other type of clocks, which are logical clocks, and let's see how these are different from physical clocks. So in logical clocks, we do not talk about when this thing has happened. We usually talk about that A happened before B. That's what we want to figure it out, if event A happened before event B. So Leslie Lamport gave a definition on how we define A happened before B and what are the various rules. Let's go over these rules. So the first one is that on the same machine, so if A has occurred before B in the same machine, that means A happened before B. Okay, this is pretty logical. Like A occurs before B, that means A has happened before B on the same machine. So if you're sending a message from let's say you have a machine A and then you have a machine B, you are sending a message, right? And you send the message was event A, receive message was event B. So it is clear that A would have happened before B. I mean, you cannot receive a message which isn't sent to you, right? So this is what it is talking about. So a message cannot be received before it is sent. So this also defines A happened before B in case of sending a message. Okay, and these are transitive. That means if you say A has happened before B, B has happened before me, then it follows that A would have happened before C. This is pretty logical, right? So now we'll go over Lamport clocks. Okay, so let us see how these work. Okay, in this, each computer maintains its own counter, small counter. Okay, and there are rules to this counter. Okay, let's see what are the rules. So before executing any event, the process increments its own counter. So let's say it was 1, it is 2. So if there is any event, then this counter is increased by 1. This will become 1 and this will become 3. Okay, another is when the message is sent from one system to another, right? This system should send this clock along with that message. So it will be M comma C. Let's say C is a clock. So that is another thing. Whenever you're communicating with other system, you send your counter, which is your logical clock of the system. Okay, that is the second thing. Now the third is whenever you receive, okay, whenever you receive a message, what you would do is your clock would become max of what you received, which was 1 in this case, and whatever is your logic clock, which is 2 plus 1. So it will become 2 plus 1. In this case it will become 3. Okay, we'll do a dry run now and let's see, this will become more clear why we are doing this. So in summary, each system has their own counter. Okay, when you send a message, you send this counter along with this message. When you receive a message, you take the maximum of both and then add 1. Okay, so this is being done to move the logic of time forward, right? So that's the logic behind. So when you're sending a message, then this event A, okay, with event A is that computer A is sending a message, and event B is that B is receiving a message. Of course this has happened before B received it, so that's why we have to increase it by 1 to showcase that the event B has happened after event A. Okay, so now let us see an example of logical clocks with 3 processes, P1, P2 and P3. So we have 3 processes, P1, P2 and P3. Let me create these, and they have their own counters. Okay, initially the counters are all 0 at step 0. Okay, at step 0 all 3 are 0. And step 1, what is step 1? It is a P1 internal event. Okay, and what do we do in an internal event of a process? We increase the counter of that. Okay, I also mark here the steps. So we increase by 1 because this is only P1 event. P2 and P3 remain same. Okay, now let's see event step 2. So that is a P2 internal event. Okay, so in P2 internal event, what we would do is we will increase the counter of P2 by 1. So it was 0, it will become 1. Now moving on, so P1 sends a message to P2. So this happens at 3, step 3. So when this is sending a message, okay, this is a P1 event, right? We'll increase P1 by 1, but these two will remain same. Yeah, do not get confused that this guy has received a message and we are not incrementing right now. We'll do that that will be a next step, okay, when it receives. So next is what? P2 receives a message. Okay, so P1 didn't do anything. It sent a message, but that was a previous event. Now P2 receives it. Okay, now pay little attention here. So when this receives it, it will also receive the clock, right? It will also receive a clock of P1. So the clock of P1 was 2 and its own value is 1. So maximum of both is 2 and then we add 1 to it. So it becomes 3. So if you see here closely, right? So this P2, I mean the event 4, right? It is what this event is. Event is that P2 is receiving a message. So naturally it would be more than this, right? This event which is sending a message. So this tells that, okay, this event 3 happened before event 4 because not because, I mean, if we can directly see, right? So that's why these logical clocks we take a maximum because we want to show that this has happened later than the sending of message event. Okay, so now there is one more last event we see here, it's 5. Okay, this is P3 internal event, so nothing to do with P1 will remain same, P2 will remain same, but P3 will increase by 1. Okay, so now let me define one thing, which is concurrency. What is concurrent events? So if you cannot say A happened before B, okay, you cannot say this, and you cannot also say that B has happened before A. Okay, then A and B are concurrent. Okay, this is the definition of concurrent event. So in this case here we see that message P1 happened before B, right? Why we can say that? Because the Lamport time of A is less than B, which was 2 is less than 3. So we can say this happened before this. But the opposite of this is not true. That means if the clock time A is less than clock time of B, we cannot say A happened before B. Okay, so this is causing that, but reverse is not true. Okay, so I'll show you example why this is not true and how this is. So if you see P3 internal event, it is 1, but can we say this 5, step 5 happened before any of these? This is a separate event which is independent of P1 and P2, so we cannot say if this happened before or after. So then that means the event 5 is concurrent with 3 and 4. I mean, it is concurrent with all of these, but let's say this is concurrent with 3 because we cannot say if this event 5 happened before 3 or after. Similarly case with the 4. Okay, so this is the problem with logical clocks, Lamport logical clocks, where we cannot say if for concurrent events we cannot find out, okay, if this has happened, although this is in the system, but we cannot still say if this happened before 3 or 4. So that will be covered with the help of vector clocks, which would help us prove that this event uh, happened before or after. Now we will cover vector clocks. Okay, so in the previous example we saw we were not able to say that event 5 happened before 3 or 3 happened before 5. Okay, we were not able to say with the use of Lamport logical clocks because this was an independent event. Now we'll see how vector clocks help us to predict this. Okay, so similar to uh, Lamport logical clocks, in this also we have counters, but we have that counters as a vector, as an array of items. So one entry for each process in the system. In the previous example we had 3 processes, so the clock would be an array of 3: P1 counter, P2 counter, P3 counter. Each system will have this, similar to Lamport clocks. Okay, so here are the rules for vector clock. Whenever process has an event, it increments its own counter in a vector. Okay, in a vector it would represent, right, let's say we have 3 and A is the one which belongs to this particular machine, so it would increase this counter and leave other two as it is. When a process sends a message, it includes entire vector timestamps. So similar to the Lamport clocks, when it sends a message, it will send this entire vector to another process. Okay, when a process receives a message, it first updates its vector by taking the element by element maximum of its own vector and one it's received. Okay, let's see this with an example. Let's say you have a comma b comma c, and then you have d comma e comma f. Okay, so what it would do is it would first take the maximum, so it will be max a comma b, okay, comma max b comma e comma max c comma f. So we are taking maximum of each one of these corresponding counters in a vector. Okay, and after that what we will do is we will increase whatever is relevant to that particular process. If it is a P3, we will increase this by 1. Okay, that's what is the rule for vector clocks, the algorithm says. Now let us go over this table, which is similar to the previous one, but this is using vector clocks instead of Lamport clocks, and see how it works. So initial state, right? Initial state all zeros. P1 internal event. So internal event is of P1, so we increase the first one, which is corresponding to P1 by 1. So it becomes 100, others remain same. Now next event is P2 internal event, right? So P1 remains same, so event is P2, so the counter responsible for P2 we increase by 1. Okay, and then you have E3 event. P1 sends message to P2. Okay, P1 sends message to P2. So when sending a message, right, it would increase its counter by 1. It was 1, now it is 2, and these two remain same because there is no event for P2 and P3. Now E4 event, P2 receives a message. Okay, now receiving a message, this and this remain same, right, because it is a P2 event. In P2, when it receives a message, what it will first do is that this formula we did, right, maximum of corresponding values. So 2, let's see here, here's the max, right? So 2 0 maximum is 2, 1 0 maximum is 1, 0 comma 0 maximum is 0, so the value becomes 210. But then you have to increase now by 1, right? And which is this event? This is for P2, that is the middle one. So we increase this by 1, so it becomes 220, right? I hope this is clear. Now we have a E5, which was a P3 internal event. So these P1, P2 remain same. P3 we increase by 1. Okay. Now we will see in this, we will be able to say, okay, P3 event is concurrent. Earlier we were not able to say that. That was the limitation. Now, how do we compare to vector clocks, right? So if A has happened before B, all events in A less than equal to B, okay, all events should be less than equal to B, and at least one should be strictly less than B. So then only you can say A happened before B. So if these are the events, A1, A2, A3, B1, B2, B3, then A happened before B if and only if all these three items are less than equal to the corresponding values in another vector, right? And there is another condition, one inequality is strictly less than. Instead of less than equal to, one value should be just less than the other one. Then only we can say A happened before B. So similarly we have this B happened before A if and only if. It is the same thing but in the reverse order we are saying it. Okay, so now the definition of A and B are concurrent. This definition was not there in Lamport logical clocks, but we have in this one. If we cannot say, we have covered this definition before, if we cannot say A happened before B or B happened before A, which we were not able to do before, then A and B are concurrent. Okay, which actually means that some components of A are greater, in A are greater, some components are in B are greater. So we cannot conclusively say that A has happened before B or B has happened before A. Okay, so that means A and B are concurrent. So in above table, right, so E3 was an event where P1 sends a message to P2. E4 was an event where P2 receives a message from P1. So E3 and E4. Let's see what these values are. E3 and E4. E3 is 200 for P1 and 220. Okay. So I've copied those values here. Then E3 has happened before even because, if you see why, because all the values in E3 are less than equal to E4, right? And there is one more condition we need at least single value which is strictly greater than in E4, and we have it, right? 2 is greater than 0. It is not less than equal to, it is 0 is less than 2, other way you could say that. So that means E3 has happened before E4. So all values should be less than equal to, and there should be one value which is just less than the other one. Okay. Now we'll see the concurrent thing, right? This was the main limitation for Lamport logical clocks. So neither of this would be true, we'll see, right? I mean, we cannot say VA happened before VB, VB happened before VA. We will not be able to say this. Now let us see how we find concurrent events, right? So the event E3 was E3 event above is P1 sends message to P1. Okay. and E5 is internal P3 event. So these are the values. Okay, this one is wrong. It should be 001, although okay, this should be 001. So this I copied. So if you see here, right, when we compare this, the first values of these two vectors, 2 is greater. So this looks like E3 happened before E5. Okay. Then when we compare the last one, then we see 1 is greater than 0. This tells us E5 is greater than E3, right? So we are not able to say any of these. Okay, and if we are not able to say any of these, that means E3 and E5 are concurrent. Okay, this is the rule here we did go through before. If neither of above is true, that means if we cannot say A happened before B and B happened before A, which is the case for us in E3 and E5 event. We see why vector clocks are not used, although they are better than Lamport logical clocks, but why they are not used? Because these vectors, right, they become huge in size. So that becomes a problem. And because of this, we have a different kind of clocks, which are hybrid clocks. These are also used by cockroach DB. Okay, and these are the combination of what we have learned in our previous logical clocks. So how they are defined is they use both the things. Okay, they use the physical time and they also use the logical counter. When it is not possible to find if A event has happened before B just based on physical time, then we use logical counter to break the tie. Okay, and combination of logic clocks, and okay, this is just an example. So what is the idea behind this? Use physical time whenever possible. Okay, if we are able to predict the events with the physical time, we just go ahead and do that. And logical increments only when physical is not enough to preserve ordering. So this would be clear how it is actually implemented when we'll go over the code for hybrid clocks. So HLC algorithm, now we'll go over this algorithm. So each node maintains, similar to logical and vector clocks, here also each node maintains a clock which is a combination of physical time and logical counter, right? And then what is the last physical time? It is the largest timestamp that node has seen. Okay, this is always the largest. Okay, and logical counter, this is which I explained before, right? A tiebreaker when physical time alone cannot preserve ordering. So we'll see like this point when we use logical counter. Let's go over a code. Okay, and let's say this is on the local event. Okay, this is a local event on the same machine when things happen on the same machine. So we get the time now. Okay, we check the now time if it is greater than the last physical time, right? So last physical time was like say 5,000 something, some Unix timestamp, right? Now is greater than this. So that would mean the time is moving forward and we are good. We are fine. If this is the case, we do not need logical clocks. Okay, then we mark the logical to 0, right? And the last physical time will become now. Last physical time, by definition, what it is the maximum greatest time, largest time, which we have already seen until now, and if this is greater we just assign it, right? So this is the case 1, physical time move forward. This means we are good. Okay, now there is another case. Okay, this case would be either it is less than or it is equal to, right? So that means the physical time is not moving forward. So when this happens, then what we would do is we will increase the logical time by 1. Okay, because if we use the same physical time, two events could get the same time, breaking ordering, right? If we use the same, okay, at this point we are not changing the last physical time, right? Last physical time is not changed, it will remain same. So if that thing will remain same, then how we'll say this event has happened later than the previous one? Because when the physical clock time is same, we'll compare the logical clock, and that clock we have to increase by 1. Okay, so let's now see and look at the pseudocode for sending a message, right? When we are sending from one to another, one machine to another. So local hybrid logical clock is HLC is, this is physical time, this is logical, and I mean P logical local and logical local, and this is physical remote logical remote. Okay, remote which came from another machine, and this is your kind of current time, actual time of this particular system. So now we see here is new physical is maximum, we take maximum of these 3, right? And this is the code which I'll break here into pieces and explain different parts. So this you have to keep in mind, that new physical is max of these 3 because time should always move forward. So okay, and all physical times equal. Okay, all 3 are equal. So that means the time, physical time is same remote and locally. So when the physical time is same, then what we would increase? We will increase the logical time to differentiate the events. So that's why we take a maximum of local logical, remote logical, and increase by 1. That's what is assigned to logical. Okay. Now another is, this would ensure that receive event is greater than send event, because the remote time and local time is same. If both the times are same, then how would we say that the receive event is greater? We can only say if the logical clock is increased or is greater. So that's what we do here, right? Now the next case is local time dominates. Okay, that means your node is already ahead of time. Our node is already ahead of time. So if it is ahead of time, then what we will have to do is we will have to increase the local logically forward to fix that thing, right? And similarly the case is with the remote. Okay, if new physical is equal to the remote physical, then we increase the logical based on the remote one. So this should be more than the remote one. In this one, this should be more than the local one. Okay, and last is the case where everything is fine. Wall clock move ahead, so time has increased and it is going forward. So in this case we have seen what we do. We do not do anything, we reset the logical, it becomes 0. Okay, real time advances past both clocks, logical tiebreaker not needed anymore. In all other cases we needed a logical tiebreaker, but in this case, because the time is moving fine, then we do not need logical, we mark it as 0. Okay, this was a hybrid clock which is used in CockroachDB. Now I'll briefly explain the weight bound in Google Spanner. Okay, so what Google Spanner does is they use atomic and GPS clock, okay, in the true time, and this true time it returns a interval of time t1 and t2, and the actual time is somewhere in between uh, t1 and t2. Okay, and when they are not sure what the actual time is, the spanner would wait until T2 to commit the changes. This in detail I'll cover in another video, but this is just to give an introduction how real life production systems use time management in distributed systems. And real global time is somewhere between, right? Spanner would wait to commit until T2. Even if spanner is ready to commit, it will not commit until T2, and it will tell all its read replicas that you also would commit at this with this time stamp T2. We'll cover this later. One quick thing is that they are fine with the little bit of increase of latency in favor of strict serializability. Okay, that's all for this video. I think we have covered a lot on time in distributed systems. I'll see you in next video. Thank you.